form and beta might be a Q form, here's how it goes. It's d alpha wedge beta plus minus 1 to the degree of alpha wedge d beta. So it doesn't depend on the degree of beta. It just depends on the degree of alpha. But this is it's called the graded Leibniz rule.
So it's not a derivation.
It's not a derivation. Oh man, I am the worst cameraman today. Over here, my bad. So, yeah, is alpha a derivation? I don't know. I thought the exterior derivative is not a derivation. Then no. I guess it might be like a. Well, even so, it's not on. A derivation is a linear mapping from a vector. It's an endomorphism, right? It's a vector. It's a mapping from the vector space to itself again. And here, if you were going to understand it as like a derivation, you'd have to be working on like the exterior algebra with the direct sum of all of these together. Maybe you could say something there in terms of, formal algebra. But okay, so that's number 2, graded Leibniz rule, and number 3. And it's been said that this is this single equation is all of physics, and that's kind of an absurd overreach, but it's not that wrong either. There's so much that can be folded into the fact that the exterior derivative of the exterior derivative is 0. So let's prove these. I'm not going to prove linearity because it's boring, okay? But I'm going to prove number 2. So if we have the exterior derivative of alpha wedge beta, all right? That is the exterior derivative of the sum over, let's say, I and j of alpha I beta j dxi wedge dxj, okay? I had more combinatorial nuance to try to make the definition in terms of a basis before, but after the dust settles, this is what the wedge product is. You have distributive property and you just wedge the differentials. That's the wedge product, okay? And by property 1, or rather its inductive extension, I can pull the sum out. All right? So I've got the sum over I and j of the differential of the product of these functions. Now, these are real functions, real valued functions, I should say, on the manifold, right? And this is the sum over, let's say, I and j, the sum over k. So these I and j are multi-indices. K is just going from 1 to n, okay? I guess we're in, or m, whatever. What do you want? Your choice. What would you like the dimension of the manifold we're working on to be? You got 2 choices, m or n?
No.
M? Okay. M it is. There we go. And so we've got partial xk of alpha I beta j dxk wedge dxi wedge dxj. But you remember what we proved about the derivative on a manifold. We proved it satisfies the product rule. It's true here. So what's the product rule give me? Well, the product rule here gives me partial alpha I partial xk beta j plus alpha I partial derivative of beta j with respect to xk. That's all what goes in those brackets there, right? But then we can rewrite this as two sums. See, we've got the sum over I and j, the sum k equals 1 to m of, and my bad, what's missing here? Oh, it's already there. Never mind, it's not missing. It was here. I just forgot it's there. Great. So we've got, partial alpha I, partial xk, beta sub j, dxk, wedge dxi, wedge dxj, plus the sum over I and j, actually, fine. The sum over I and j and then the sum over k equals 1 to m of alpha sub I, partial beta j, partial xk, dxk, wedge dxi, wedge dxj. All right. Give me a second. I gotta erase myself some spots. Some space here over here. So, what can we do here? Let's rewrite that. So we've got d alpha wedge beta is equal to what? Well, we've got all this stuff here, right? Basically, what I want to do is point out that we can just use properties of the finite sum and everything and rewrite that as the sum over I. All right. Sum over k equals 1 to n of partial alpha I, partial xk, dxk, wedge dxi, wedge sum over j. Notice that there's no j dependence in any of this. So I'm just using the distributive property here of the wedge product. And I can bring the beta j over here, dxj, all right? And then plus what? Well, plus the other one, all right? And the other one, well, there's a problem. The problem is, I'd kind of like to do the same thing, but here, I need this dxi, I need to move it over to here, but when I do that, it costs me, the cost is permuting the dx. So basically, I need to make a comment here somewhere. I'll do it here. So dxk wedge dxi is equal to -1 to the number of things in I, dxi wedge dxk. Notice dxk is a single differential, right? So over here I've got plus -1, and what is the number of things in I? Well, that is exactly what we call the degree of alpha, right? The number of indices in I is the degree of alpha. And we'd have the sum over I of alpha I dxi, all right, wedged with the sum over j, sum over k equals 1 to m of that stuff down here. Let me, I need a bigger room. I can't zoom the camera back enough to get all this at once. It's okay. But anyway, well, so all I'm doing, at the moment is I moved commuted the differential there, right? And now I'm going to, again, use the distributive property of the wedge to move this stuff over here. And you've got what? You've got partial beta j, partial xk, dxk, wedge dxj, right? But what is this? This all here is d alpha. This right here is beta. So you've got d alpha wedge beta plus minus 1 to the degree of alpha. This, of course, is alpha. This is d beta. And that is the graded product rule. So it's not, well, I mean, if you have the right notation, it's not that bad. Understand that if I did this proof not using multi-index notation, it gets less fun. Yeah. Yeah. So what's the proof of 3 look like? How do you think I should do that one? Let me start out easy. Let's do it for 0 form. The claim is that that's true for, what this means is, this is a notation for saying that d of d alpha is equal to 0 for all p forms alpha. So the base case would be a function, right? So consider p equals to 0. So if we consider the p equals 0 form, we're looking at d of df, right? Which is the differential of the sum k of partial f partial xi, rather xk dxk, right? Which then, by definition, is the sum over k, right, of the differential of the kth partial derivative, right, wedge dxk. But this is the sum over, let's say, k and j.
We're going to have double wedge.
Let's see here, partial xj, partial xk, dxj, wedge dxk. What'd you say?
Are we going to have like double wedge that cancel each other?
Something like that. So here's the thing. I can write this as equal to the sum over, let's say, L, other indices, kj. How about I and L? I and L of partial squared f, partial x, I don't know, I, partial xl, right? Dx I wedge dxl, right? But I know that dx I wedge dxl is minus dxl wedge dxi, and I know that partial squared f partial xi partial xl is equal to partial squared f partial xl partial xi. So this is minus the sum over I and L of partial squared f partial x L partial xi dxl wedge dxi, right? But then if you just switch the indices back to where we started, we've got this is equal to minus itself, right? Just changing the labels again. Anyway, the point is, once you have this, it's clear it sums to 0 because this is symmetric in J and K, whereas this is anti-symmetric in J and K. And whenever you have a contraction of two tensors, and you have a symmetric pair of indices in one and an anti-symmetric in the other, its contraction is 0. It doesn't matter how many other indices are out there. If you've got a pair of symmetric contracted against a pair of anti-symmetric, it's gone. Anyway, hooray, it's 0. So, okay, that's great. How about, but there's more than just p-forms, isn't there? So suppose inductively. Inductively suppose, right? Assume that d squared equals to 0 for p-forms, right? And let alpha be a p plus 1 form, right? If we have d of d alpha, what do we get? Oh, that doesn't help. I was thinking induction might do it here, but now I'm starting to... Maybe I'm just completely wrong. Is induction the way to go here? I don't think induction's helping. I think we should just calculate. So if we have a p-form, right? Sum over I of alpha I dxi, a p-form. Then d alpha is equal to, of course, the sum over I of d alpha I wedge dxi. So d squared alpha is the sum over I of d alpha I wedge dxi plus rather minus the sum over I of, listen, I should just leave this sum out here like this, okay? My bad. So I'm taking the derivative of this. So d alpha of I wedge dxi minus alpha, my bad, minus d alpha I wedge d of dxi. All right? We already proved that this is 0 because alpha I can be equal to f. That's a function. This is the second derivative. This is d squared on a function. We already have shown that that's 0. So if we knew that d squared of a differential is 0, or d squared of a coordinate function is 0, this is 0, right? Oh, but actually, that's funny. This is also d squared of the xith coordinate function. Oh, that's not true. That's not what that is it? That's a lie. It's not that. That's just my notation deceiving me. This is the differential of dx I1 wedge dx, I2 wedge wedge dx IP, right? The question is, why is that 0? Well, that's 0 because by definition that is like partial xk, right? of, well, goodness gracious, how to express this. Okay, fine, yeah, partial xk of 1, right? Times dxk, wedged with dxi1, wedge wedge dxip. Sum k equals 1 to m, right? So what's the component function here? The component function here, it's hard to see, but it's right there, it's 1. So this is a differential form. Its exterior derivative is the partial derivative of this times that, which of course is 0, which makes this 0. If I was going to formally define the exterior derivative, one of my things I would be tempted to put as an axiom was that the d squared of a differential, like d squared of a function is 0. That's true whether we're talking about a function like f or the coordinate chart function, right? Like, it is also true that d squared on dxk, right? That's, excuse me, d of dxk is equal to 0. Anyway, altogether, we have 0. So, hooray. That's the proof of 3. It really mostly is the first thing. Like, the first thing is the biggest hurdle once you have that. Okay, so what happens if we put together this calculus with the work form and flux form correspondence stuff we talked about earlier today? We should be able to find identities for the curl and the divergence that are stemming from these applied to the flux and work form correspondence. The easiest ones of those are the ones from like d squared, and you may or may not be familiar with those. So, for instance, let's see, let me recap. We had, what's that? Oh yeah, thank you. To recap, what were the 3 things we found? We found that the differential of a function was the work form of the gradient. We found that the differential of the work form of a vector field was the flux form of the curl, right? And we also found that the exterior derivative of the flux form of, let's say, a vector field G was the divergence of G, right? Dx wedge dy wedge dz. Oh, thanks. So, this being the case, what does d squared equal to 0 tell us? So, like, let's see this one. D of df is equal to d of omega gradient f, right? Which is 0. But this is the flux form of the curl of the gradient is equal to 0. So therefore, the curl of the gradient is equal to 0. Because, by the way, the flux form is an isomorphism. It's only equal to 0 if the thing that's going into it is 0. It's an injective thing. So if you take the exterior derivative of this, what do you get? You get the divergence, well, I'm sorry, you get the exterior derivative of the flux form of the curl, right? Which is the divergence, yeah, down here, the divergence of the curl, right? Times dx wedge dy wedge dz. So therefore, the divergence of the curl is equal to 0. Now, if you've studied vector calculus, you've seen these identities before. They're super useful on tests and such. And I think this is where the story stops. See, because it's true that the exterior derivative of the flux form of the exterior derivative, I mean, it's true you can take the exterior derivative of both sides and get 0 here, right? But it's not interesting. Why? What is the exterior derivative of a 3 form on R3? It's a 4 form. What are the 4 forms in R3? Well, they're 0. Because 3 form is the top form on R3. So this being interesting stops right here. You just get these two. Now, but we can play other games. We can play other games. Remember we found this before? We found like omega f wedge omega g, right? Was equal to, what was it? The flux form of the cross product, yeah? So what happens when we differentiate this algebraic identity? Let's try it. See, we'll get d omega f wedge the work form of g plus, well, excuse me. Do you understand why I put a minus over there, by the way? The reason I put a minus over there is because we were taking, it was a 1 form. So the degree was 1. Minus 1 to the 1 is 1, minus 1. And here also, I'm taking the exterior derivative of a wedge product of a 1 form and a 1 form. So the graded Leibniz gives me a minus. Essentially, it costs me a minus to pass the d past omega f over to the dg. So I get omega f wedge d omega g. And on the other side, of course, I get the exterior derivative of the flux form of the cross product, yeah? And this, well, is the flux form of the curl of f, wedge product with the work form of g, minus the work form of f, wedge product with the flux form of the curl of g. And of course, on the other side, we have the divergence of the cross product of f and g. And of course, you've got your handy dandy dx wedge dy wedge dz. But do you remember what we proved about this? I'm not sure I do, but I think if I remember right, when we took the wedge product of a 2 form with a 1 form, we got the dot product of the things being wedged times dx wedge dy wedge dz. So if I'm not remembering wrong, this is exactly curl of f dotted with g minus f dotted with the curl of g. All of that times dx wedge dy wedge dz. Well, there you go. That is a probably less known vector identity, but it is true. The divergence of a cross product is the difference of the curl of the 2 vector fields dot product with each other respectively, with that minus there. And that minus is there because of the graded product rule of the wedge product. Is there anything else we could do in terms of the things we have explored here? Is there any other interesting product we could study derivative of? Oh, I can think of one. How about a function? What if we do like a function times the work form, or a function times, we could do like the scalar multiplication, right? You know what I'm talking about? Let me write it out. Once I write it out, you'll be like, oh, okay, obviously, like duh. How about this, like a function, a 0 form, right, times the work form of g. That is a meaningful product. It's actually a wedge product of a 0 form and a 1 form. We just don't write the wedge product for the 0 form product as a matter of custom. Now if we exterior differentiate that, I don't know what that's going to tell us. Maybe nothing, but this would be df wedge omega g, right, plus f d omega g, right? Now, oh, here's the thing that makes this interesting, is can you tell me, this is the same as the exterior derivative of omega times a what? What the work form of f times the work form of g vector field, it's the same as the work form of fg. Search your heart, you'll find it to be true. See, because it's an isomorphism. It's in fact a linear mapping, so the scalar multiplication pulls in. And I say linear mapping, but I should really say over a ring. More on that next semester. Anyway, so pulling the f in like that, and this over here is what? That's the work form of the gradient of f. Wedge that, right? And this here is the flux form of the curl of g, is it not? And this is the curl, excuse me, it's the flux form of the curl of f times g equals the flux form of the cross product of the gradient with g plus the flux form of f times the gradient, because remember the flux form is also an isomorphism. You can pull scalar multiplications inside it, like so. But this is an isomorphism, so you can add this plus this, and lo and behold, you get the identity. The curl of f times g is equal to the gradient of f cross g plus f times the curl of g. Which is a vector identity that you can prove in vector calculus with some effort. More effort than we just made for sure. See, yeah, there's a lot here. I think there's probably more we could do, but maybe there's something in the homework you'll find that I haven't done yet today. Feel free to redo these in the homework if you want, just so that they become yours and not just mine, right? You need to take ownership of them.
That'd be great.
Yeah, yeah. But that's the wedge product. So the wedge product simultaneously folds the gradient, the curl, the divergence. It's all in this one unified algebraic operation. And we'll see as we go on here that there is so much more we can do with it. Now, I have a proof of coordinate independence on page 241. I'd rather not do that in class this semester. I may feel obligated to do it next semester. But next semester we'll be in a room with a projector, at which point I'll be able to project it and say that I did it. And here the projector is sketchy at best. This is a very good place for us to stop. So we're right now to the pullback. The pullback is the partner to the push forward. Pushbacks and pull forwards, they work together to move tensors from one space to another. When you have a manifold map from one manifold to another, you can use the pullback and the push forward to push vectors from the one space to the other and to pull differential forms back from one space to the other. And it's very cool. Anyway, we will do things with it. Anyway, thanks.